Okay, so the idea for today is just to continue talking about integration involving like trigonometry. So like before like the day before the exam, we had already talked a little bit about that. But now we're going to do something that's called more like trigonometric, you know, substitutions. So for that, let me show you what's about to happen. Okay, so these types of integrals work for when you have expressions that look like the following. And now I'll do an example of each type and kind of like try to explain what the idea behind it is. But this technique works when you have integrands and so essentially, I guess like the other one is like we should have put like let's put like a minus here. So essentially, here A is like a constant. A is a constant here. So it involves essentially like differences or sums of squares, basically, where where one of the terms is x squared. Um, so to kind of like before writing a specific example, let me kind of give you the motivation behind it. And the motivation behind it is Pythagoras theorem. So Pythagoras theorem is probably top 3 important theorems in mathematics. So let's just kind of quickly say something about Pythagoras theorem and trigonometry, right? Or motivation. So Pythagoras says that if you have a right triangle, A, B, and C, like actually. Then what, and like C, I'll read, I'll leave that one to be always like the length of the hypotenuse. So what the theorem says is that C squared equals A squared plus B squared, right? So the length of the hypotenuse squared equals the sum of the squares of the other two sides in the right triangle. Okay. Just to mention it because it's kind of like an interesting thing to say, because it may not have been mentioned before, like when you were told about this. This is like literally a formula between squares, right? So if you have the idea is that, if you take this side, right, you can build a square, whose lengths, whose sides have length A. If you take the second side of the right triangle, you can build a square whose sides have length B. And if you take the hypotenuse, you can build a square, right, whose sides have length C. right? And what is the area of the like the first square? The area of the first square is like a squared, and the area of the second square is b squared, and the area of the third square is c squared. So essentially, what Pythagoras theorem is, it says that if you add the area of these two squares, you get the area of the third square, right? So it's like that's actually how like the Egyptians and the Greeks and all like ancient civilizations proved the theorem. So they thought about it as a statement about like literal squares, which is not something that we need, but it's kind of like a cute historical fact. In fact, I don't know if you have seen it's like a 1 minute YouTube video, but it's kind of super like I'm teaching this intermediate algebra class, and so I showed it to my students and I find it very cute. So I'll show it to you. So you can demonstrate this like with water, essentially. So basically, like here's like a right triangle. Let me turn off the lights quickly, because it's really fun. Okay, now this made it worse. How do you turn off the other lights? I have no idea. Okay, doesn't matter. So you have a right triangle here, which is the yellow one, and I don't know if you can see like these two squares, right? So they're filled in with water or a liquid of sorts, and then you have like the other square, which is completely empty, corresponding to the length of the hypotenuse, like the square built from the hypotenuse. So it's like a very clever physical proof of the theorem. And then the hypotenuse square is going to be filled in with like, and then that's like your physical proof of Pythagoras theorem. Like like the liquid of like the two smaller squares make up the liquid for like needed for the larger square. And so that's kind of cute. Like of course there's like a mathematical proof for it. Which are like there are tons of proofs of Pythagoras theorem. Like I think even now with machine learning, like judge like they have like the computers have found their like independent proofs that no one had else like thought before. So it's kind of like something where like you can always like find like a clever way to think about it. Now the reason why I do mention like I did want to talk about Pythagoras theorem is that you know what this is saying is that whenever you have a sums of squares, there's secretly a right triangle involved. That's how you should think about the theorem also. So what this is saying is that whenever you have the sum of two squares, you can build a right triangle, basically. And you'll see that that's actually like a useful perspective to have like when we talk about these integrals. And then the other thing like that we will, so again, like that's kind of like the most important thing about Pythagoras theorem, that it is related. The right triangles are related to sums of squares in some way. And the other thing that's important about it is that you can define the trigonometric functions in terms of right triangles, right? So if you have like a right triangle, I'll just put the three basic ones because that's all that we will need. If you have a right triangle, then the sine of theta is b over c. The cosine of theta is a divided by c. And the tangent, which is also useful for these problems, the tangent will be b divided by a, right? So these two things will come in handy in a moment. That okay? So far, so good, making sense. Okay, so let me start with like an example of like the type of integral we want to solve and how that relates to this. Um, and then I'll give you like a more of like a recipe, but it's kind of like useful to start with an example to see what's going on. So let's say you wanted to integrate Okay, so the idea is that if I'm bringing it up this integral at this point, is because like anything that you have learned thus far does not really work really like well with this. Like, so use up will not be that useful. Integration by parts would not be that useful. Like, so the idea is like basically everything else you haven't seen before, like either fails or would take like an insane amount of time, like, so to try to integrate it. So you want to be creative, and of course, like whoever found this for the first time, like you are like, okay, how would you ever have come up with that? But then, like, that's why it gets thought up, because you are not expected to reinvent the wheel. Like, so like the trick is like, because this involves like the square root, I will just call y the thing that involves the square root. Okay, so here's like the trick. Just to understand this quantity a bit better, like, and you'll see that something like magical happens here. So if you call that y, then what happens? I can square both sides of that equation, right? And if I square both sides, I get y squared equals 9 minus x squared, right? And then if I add x squared to both sides of the equation, I get x squared plus y squared equals 9. So I'll stop here, give you a second, write this down. Is that okay? Makes sense so far, so good? Okay, and now back to what I was saying. Oh, you're adding two squares. Every time you add two squares, Pythagoras is involved. So you write this equation secretly is like a Pythagoras theorem type equation, right? Like, because you can make a right triangle whose sides are x and y and whose hypotenuse is 3. So secretly there was a right triangle in this problem if you can like introduce the right variables. So let me draw the diagram here. So like the side, like, like it does, like what there's definitely sure is like the hypotenuse has to be 3, right? Like that's which side gets called x and which one is called y is more like arbitrary. Okay, just like because like this is horizontal, I'll call this one x, but that is kind of more like up to your preference. But so what I'm saying is that this is like, if you think of the right triangle, this is x, this is y, and this would be 3. And yeah, Pythagoras says that x squared plus y squared equals 3 squared, so like x squared plus y squared equals 9. And the reason why this type of integrals are called trigonometric substitutions is that you want to use trigonometry, okay? You want to use trigonometry to kind of like replace x. So you don't want to work with x directly, you want to work with something defined in terms of the angle theta. So you had this angle theta, right? And okay, and so if you think about like the trigonometric functions that we were talking about before, right? If you use sine of theta, that has to do more with y, right? Y over 3. If you use cosine of theta, that's nice because that involves x and 3 is just like a number. If you use tangent, that is y divided by x, so that involves both y and x. And you want to do kind of like the substitution that involves the least amount of variables, like that's kind of like the most efficient. So work with the fact that the cosine of theta, right? So cosine of theta is x divided by 3, or x equals 3 cosine of theta. So this is kind of like an analog of a u sub, right? Where instead of like saying like, I mean, it works kind of like like in the same spirit of a u sub. But now like the idea is kind of like I will substitute x with something in terms of theta. And so that's kind of what we were going to do. And we will rewrite the integral in terms of everything we rewritten in terms of theta. I could have called this x equals cosine of u, but it's kind of less transparent what's going on because I do want to think of the variables as an angle. So that's why I'm calling it theta. But the thing is like once you get to this point, then it really almost collapses to a u sub type problem. So like there's not much, anything else is kind of like the same as that.
Sub in 3 cos theta for x.
Mhm.
Can we just switch that dx to d theta?
Well, that's exactly what we're going to do, just like as in the u sub. So what would be the x? dx, it would be -3 sine of theta d theta, right? Because it works in the same way as right, because the derivative of cosine is negative sine, so it would be -3 sine of theta d theta. Does that make sense? So far, so good. And so let's just plug everything in to see what happens. So so what happens with this expression? This becomes okay. So 9 is still 9. What is x squared? X squared becomes 9 cosine squared, right? So you get 9 cosine squared of theta. What is x squared? X squared is 9 cosine squared of theta. Oops. And what is dx? Let me use a different color like here just to make the substitution more clear. So dx is -3 sine of theta d theta. So dx is -3 sine of theta d theta. Okay, so far so good, making sense. And you'll see if you keep like playing with the like express algebra, like it will give you something that can be integrated. Right now, it's not in a format that kind of makes that super clear, but we just have to keep playing a bit with the trigonometric identities. So the first thing you can do is like okay, so we have to manipulate a bit more like the the square root to see what's going on. So like I'll write that as 9 times 1 minus cosine square of theta. Okay. And then what can we do? Okay, there's a 3 here, which can get canceled with like well, not the entire 9, but just 3 of that. So like you get 3 cosine square of theta. And then we can put like we can take out the negative sign if we like, and so we can put it like that. So that is not bothering us. And I forgot to keep writing the sine of theta, right? Like the sine of theta is still there. Is that okay? Is that making sense? So far, so good. Yeah. Oh, because
Negative.
right. Yes. Anyone else? Okay, and here, and this will be used over and over and over and over for all these problems. 1 equals sine squared plus cosine squared, right? So like magic identity also that 1 equals sine squared plus cosine squared. So when you have 1 minus cosine squared, that gives you sine squared of theta. So okay, first thing is that this 9 can come out of the square root as a 3, right? And then 1 minus cosine squared because of like the key identity, which is also thanks to Pythagoras theorem, by the way. So that is sine squared of theta. Okay, so far so good, making sense. How are we doing? And then okay, you'll see the simplification continuous, because then I'll take out the sine square as sine of theta, the threes cancels, right? So I have threes go away. So you get sine of theta from the square root, and there's a sine of theta here, so I just get sine square of theta over cosine square of theta, d theta. Is that okay so far, so good? Okay, and here now you come at this point and you have two options. So one option is to think about that as tangent square of theta, and then you have to think, oh, how do I integrate tangent square of theta? And for that, essentially, what you have to use is like this identity that what, like secant square equals 1 plus tangent square, which you get by dividing here by cosine square. The other option, which is equivalent to basically doing that, is that I'll use this like the magic identity again to write sine square as 1 minus cosine square. So I will write everything in terms of cosine. But it is more or less the same as what you would have done if you had tried to integrate tangent square. But I tried to minimize the number of identities that you should remember. So if you kind of keep working with sine and cosine until the very end, many times that kind of like makes your life easier. So I'll think about sine square as 1 minus cosine squared. Okay, and the advantage of doing it that way is that now I can break the fraction as a difference of two fractions. So I'll write it as, um, 1 over cosine squared and then minus cosine squared over cosine squared, but that's going to be just 1. I'm kind of like going slowly to show you all the steps. Oh, sorry, yeah.
Took the square root of sine squared theta, this becomes sine theta?
Right, but there's a sine of theta, an extra sine of theta. Yes, yeah. I'm combining those two. Yeah. Yeah, I can put like an arrow or something like that. So this sine square kind of comes from these two contributions, you see. Any other questions? So far, so good. Okay, and then this becomes minus, what is 1 over cosine squared? That's secant squared. Okay. And then cosine square over cosine square is just 1, right? And now each of these can be integrated easily because the integral of secant square is tangent and the integral of 1 is just theta, right? So like, because this is an integral with respect to theta. So you get minus tangent of theta minus theta plus like the constant of integration. Is that okay? So far, so good. And then we're almost done, but if this were like had been an integral in terms of theta, we would be done. But this has to be in terms of x, right? Because we started with x. So we have to go back to the right triangle. Sorry, just to go back to the right triangle that we had here. Copy paste it for a second. Okay. So that's why having the right triangle is useful. Because the idea is like, since you integrate it with respect to x, like the answer should just be given in terms of x exclusively. So how can I do that? What is tangent from the diagram? Tangent, well, is y divided by x, but again, if you go back actually to the very beginning of the problem, sorry, just to go back for a short second, to the very beginning, I had called y, I had given y in terms of x actually. So in this case, you can think of the tangent as just being, what? Let's put it here. Like it would be root of 9 minus x squared divided by x. That's what the tangent equals. So let me just put this here. right? And then, okay, so that gives you the tangent in terms of x, and then you have to give theta in terms of x. There's no way to do that without using arc cosine or like the inverse trigonometric functions. So if you go back to what we had said, like, we had said that x equals 3 cosine of theta, right? So that means that x over 3 equals cosine of theta, right? And then so if you try to solve for theta, I'll use arc cosine instead of cosine to the -1 because that can be confused with like, the reciprocal. So I prefer to use arc cosine for that. So all of like the theta gets replaced with arc cosine. And so, well, just to rearrange it a little bit because like there's a negative sign in the front. And that's the answer, for example. Yeah.
So when we did like, way back, when we did like the substitution of cosine theta equals x over 3.
Mm-hmm.
So, I mean, I can kind of see that like in this problem, like that doesn't really cause a problem with the range.
Uh-huh.
Because of the square root, it's still like -1.
Right.
Can that create problems in like other questions, like when the domain and the range don't like match, so we like concepts?
So that's a good point. Like the thing is to a large extent, well, right, like in this case, because like right, like because like the expression involved 9 minus x squared inside a square root, implicitly that forces x to be between -3 and 3, right? And that's why this substitution works. But for example, here's like a more subtle point that I didn't refer to because, if you had like, when I took the square roots, right? When I took the square root, someone could have said, well, but shouldn't that sine squared come out as an absolute value of sine, right? Because I drew the angle as being acute, right? Like in the diagram, I secretly cheated a little bit, right? Because I'm thinking of the angle like as being acute. And then someone could like worry about, oh, whether like, whether whether you have to use absolute value or not. And so what these many integrals of this form are where you call like formal integrals, where you kind of like integrate without worrying about those things. And then like, it's kind of like end justify the means kind of thing. This works. We're just trying to find an antiderivative. So you don't care how you get to the end result. As long as you take the derivative of that and it spits out the integrand, that kind of counts as an antiderivative, right? Now, for example, in order to take our cosine, right, like to take the inverse of a function, you have to restrict the domain, right? So there's like an implicit restriction to the domain already here, because otherwise you cannot, the cosine function is not like bijective, right? Like you have only on certain domain values for theta, it has like an inverse. So like already that like, restricts, like you are making certain assumptions about the range of the domain, but they're kind of like thrown under the rug. Like, no one but like, we're kind of just trying to say, oh, how would you find it if you didn't care about all of those things? But you could, of course, like care about those things. Which but it's kind of like not kind of like our object of interest at the moment, where it's just like more like formally, like, how would you find the answer if all those domain and range questions were to work as you would like them to work? Because otherwise it's kind of like too much of like a black hole, like in terms of like going into like all those details. But yeah, but kind of like that's a nice thing about an antiderivative, that at least this expression is definitely defined for certain values of x, right? We're not trying to find that for which values of x is it defined. For example, here I cannot put x equals 0, just to give you like a simple like answer. And there are other things I could not put. But whenever it's defined, if you were to take the derivative of that, then you would find the correct Is that making sense? So you don't care, like that's kind of like, and this actually what you, if you anyone has to ever take differential equations, that's what will happen if you ever take that class, because there you have to solve what you call like a differential equation. And there's so many shady things that you do as you solve them, but it doesn't matter because like there's a theorem that says it's called like uniqueness of solutions, that under certain conditions, there's like only one solution. So if you found something that looks like a solution and it is a solution, that's all that you have to like could have found. So it doesn't matter whether you did suspicious stuff in the process, because if you produce something that works, the uniqueness theorem says like that had to be the correct answer. Now here's like other important point. Sorry, before making that remark, are there any other questions about how I did this? Here's another point, which is also like useful to like notice. So remark. If you had drawn, what happens if you had drawn the triangle slightly different, right? If you had drawn the triangle as so in this case, it was kind of like clear, like that maybe I wanted X to be the horizontal side. But like, what if someone had said like, oh, let's call X the vertical side, right? Like that cannot be like, the end of the world. Like, what if and then let's call the Y the horizontal side. So based with this diagram, you would have used sine of, like, in this case, you would have said that like it would have been easier to say that sine of theta is X over 3, right? And that 3 sine of theta equals X, right? So in this case, like the natural substitution to make would have been with sine instead of a cosine, right? And how do you know which one is the correct one? And the nice thing is that either is correct. So it doesn't matter which one you use. Like the only difference that will happen is that if you go through the exact same steps, it more or less will look exactly the same as what we just did. It's just that it will have like an arc sine here. But arc sine and arc cosine are related. And so that's the thing with trig. There's so many identities between everything. So even if something doesn't look quite exactly the same, because of like all these identities, you can always kind of like rewrite them in terms of like something that make it so that they look the same. So what I'm trying to say is that here also this would have worked. Like, this also worked. It's just like psychologically, I do prefer to think of X as horizontal, and that's why I went with cosine. But if you open the book, I think they just recommend using like a sine of theta. So they use it with sine, but it's like a nice exercise to see that it actually produces the same. Like even though it would look a bit different because it would have arc sine, it also works. Also works, but it will look different since it will look different since it will have arc sine, because it will use arc sine. But that's like a minor difference again. So so the the idea, just to kind of like summarize, but I prefer to draw the diagram. So I'm not recommending to just memorize it. It's always nicer to draw the diagram first. But like to summarize, if you have something like a squared minus x squared, the idea is to use like x equals a cosine of theta, or x equals a sine of theta. Either works. It's more like of a preference which one you want to use. Like they more or less behave in the same way. If appears. Right, like the integral that we did, it doesn't involve just that. Like, but I'm just saying, if there's something involving root of a squared minus x squared, the rule of thumb is to just to use one of those two substitutions. Let's just say try, because it's not that like, obviously for the examples that we'll work with, like this will always work, but of course, you could just start putting more and more weird stuff and then everything breaks down. Is it making sense? Questions about this? So far, so good.
X squared doesn't have to be the number of X squared, right? Like it could be any number.
Right, like I mean, yeah,
It
exactly.
could be like 10.
Good call. Yeah. So for example, if I had like if I had like 10 minus x squared, then you can use root of 10 cosine of theta, right? Because of square root, anything is a square. That's the point of square root, right? Like By the way, that's actually Pythagoras, like not just to kind of like keep propping up Pythagoras theorem. That is like another use of Pythagoras theorem. That's how you construct the square roots, right? With a Pythagoras theorem, you don't know whether square roots exist or not. But with Pythagoras theorem, that's, if you take a triangle with sides 1 and 1, then 1 squared plus 1 squared equals a number squared, and that number happens to be called root of 2. But that is the only way to know what root of 2 is. And once you have root of 2, you can create root of 3 by doing like a triangle with sides 1 and root of 2. And then 1 squared plus root of 2 squared, that gives you 3. And then like the hypotenuse square will be 3. And that's how root of 3 comes out. So there's no way to construct geometrically, the only way to construct the square roots is like using Pythagoras theorem. Otherwise, you would not be able to do that. So, and that's when they found later that square root is irrational, that it was like a big shock to the ancient world because they thought like everything had to be like a ratio of numbers, so of integers, and they had like a weird like religious mythology where like the universe was made out of numbers. So there's this like weird story that the Pythagoreans were like a cult. And so there's like a story that one got killed because they revealed the secret that like root of 2 was like irrational, and like no one would think about, imagine like the politician of that time were like, oh, you'll die if you say that root of 2 is like irrational. It's kind of like an odd thing to think about. But and that's why it's called, like, when you call someone irrational, that is an insult, right? I mean, it comes from that, right? Like like rational, like, that's why it has like all these connotations. Like, a rational person is kind of like something to aspire to. If you're irrational, that is why there's this bias against, like, it's not a coincidence that the names kind of go that hand in hand, because like they were not well looked upon. And that's also why you talk about imaginary numbers versus real numbers, because again, there was a lot of like mental opposition to using imaginary numbers. So like, like the numbers like kind of reflect the period culturally of the time when they were discovered. So like that's why you call like the integers, they are also called like the natural numbers, right? So there's this thing called like the natural numbers, where it's what everyone is supposed to think about, and then the rational number, like, so it has all these like mental, like there's a lot of like hiding in the words that you use to refer to them. But that's where it kind of comes. That's why like the rationality comes, I guess, so like as an insult, kind of, because they were like a shock that was found. And ironically, there's a sense in which there are more irrational numbers than rational numbers, but that's kind of like a different story. But like, okay, here's another, and like the nice thing about these substitutions is that the diagrams always work. So you don't, if you do the diagram, you don't like it, like that right triangle will tell you what to do. That's like kind of what's fun about this problem. So let's do this one. Let's do. So you don't have to memorize any substitutions. That's what I'm trying to say. You just need to remember the Pythagoras theorem. So you just call y, that thing involving the square root. So if you square that, you get y squared equals 4x squared minus 1, right? And again, for Pythagoras theorem, you have to see it as a sum of squares. So I'll just move the 1 to the other side, because that's what will allow me to write this as the sum of 2 squares. Okay? So there's a Pythagoras theorem, there's a right triangle for you, because you're adding 2 squares, and it gives you a square of something. So the only difference is that now 4x squared is related to the hypotenuse, right? Because the hypotenuse is always the thing that's on its own, like in Pythagoras theorem. But that's what I'm saying, like the diagram will tell you what to do. Like you don't have to, like the diagram is kind of like good enough that it tells you don't memorize anything. So because like this course has so many things to memorize, you want to minimize like memorization. Like, like that's why Calc 2 has like, I think, reputation for being hard, the hardest of the 3 calculuses, actually, because there's just so much stuff to memorize. And so a lot of stuff is not so much like, the difficulty per se, although there's some difficult things for sure, but it's just like, your mind can be overcrowded with all these variations of different formulas. So the more like you can avoid memorization, like it's better. So in this case, I'll just draw my triangle as 1, y, and 2x. So if you draw the diagram in that case, right? That works because 1 squared plus y squared will give you 4x squared. And you call this angle theta, just to continue with like our convention. And again, like the idea is to use, you want to substitute x, so you want to use a trigonometric function that involves x, but doesn't involve to the extent that's possible the other variable, because you want to work just with one variable at a time. So in this case, like also cosine of theta works, right? Because if you do cosine of theta, that's 1 divided by 2x. So if you do cosine of theta, it's 1 divided by 2x. But now, if you solve for x, you get 1 over 2 cosine of theta, which is, 1/2 times secant of theta, if you want. So you see, like in terms of the right triangle will guide you. So it naturally comes out that substitution in this case involves secant, right? Where like the trigonometric function is the same, cosine, but now like the x appears in a different position because x before was in the numerator, now x is in the denominator. That's why you end up working with secant instead of like, like cosine, like in the substitution. Is that making sense? Kind of. Yeah.
Do you always call the vertical side of the triangle y?
Well, that's what I was saying. Actually, it is strong enough that like if you had flipped like that's what I did like in this remark. If you had called x the vertical one, then the natural substitution is like with sine, but it still works. Like it will always work. The only thing is like it may look different.
So it's not just for that case.
Right. Like the only thing that matters is it's not for debate, is which one is the hypotenuse. But once you decide the hypotenuse, the other two are kind of like your psychological preferences. Like, why typically, yeah, you would call it the vertical one, but like that, the math kind of like takes care of that, like, because what is vertical, what is horizontal, it's like arbitrary, you see. But yeah, what hypotenuse, like which one gets identified as a hypotenuse is what it is not up to you, because the hypotenuse is the one that appears on its own in Pythagoras theorem, like that's for sure. So, but and the thing is, like once you find the correct one, like kind of like the problem works more like automatically at that point. So like if you say that x, so I'm saying that x is 1/2 secant of theta. So what is dx? We also need dx, right? So dx, like the derivative of secant is secant times tangent, right? So like it becomes 1/2 secant of theta times tangent of theta d theta. Okay. And then let's just put all of this into the integral we were working with. So let's do the substitution. So what is the x? According to this, the x is 1/2 secant of theta, tangent of theta, d theta. And then you divide by what? 4x squared. So 4, what is x squared is 1/4 of secant squared of theta. And then minus 1, right? That is what you get if you do the substitution. Okay, so far so good. So the 1/2, like this 1/2, if you want, you can take it out. So you get 1/2 secant of theta, tangent of theta, d theta. Again, and then you get secant square of theta minus 1. Right? And the one in the denominator is going to be dealt with the magical identity that 1 equals cosine squared plus sine squared. And again, like you could memorize more identities than that, but it's really not needed, because if you take the magic formula and divide both sides of the equation by cosine squared, then you get the secant square of theta is 1 plus tangent square of theta. You know, like these are like, they're kind of like equivalent. You just get 1 by dividing by cosine square. And so secant square minus 1 will be tangent squared. Okay, so you get 1/2. Like, let me just put everything here. Tangent squared. Okay, and perfect, because then this comes out as tangent, cancels this tangent, so you're just really integrating secant of theta d theta, which is there's like a horrendous trick in Calc 1 to find that. I mean, it's like a very clever trick for like the antiderivative of secant, but like you kind of multiply by secant plus tangent on both top and bottom, and that's how you end up finding this natural log of secant plus tangent. I mean, but that one is like really shady, but like, you know, like I would, because it will appear multiple times, I guess, like that's the only reason why I would expect you to memorize it. Yeah.
Can you leave it as tan theta at the bottom and then say u equals tan theta and u equals?
Oh, but the thing is like, oh, right. That's let's see, yeah. No, but the thing is like, if you do u equals tan theta, right? Then the u is secant square of theta, right? The derivative of tangent is secant squared,
You're
right?
right, you're
Yeah,
right,
yeah.
my
No, otherwise it would have been nice, but
Yeah.
no, unfortunately, it's not that nice. I mean, it's not that bad because like, the antiderivative for secant is supposed to be known. So this just gives you secant of theta plus tangent. Okay, so far so good. And we're almost done, because the only point is that this is the answer in terms of theta. I don't care about theta. I just care about everything in terms of x. So you just have to go back to the right triangle and rewrite everything in terms of x. Okay. So let's go, sorry, just to go back to our right triangle. So this is the right triangle, which again, here we do know y in terms of x, right? We know that y was 4x squared minus 1, if I'm not mistaken. Okay, so because of like the right triangle, you can give everything that involves theta can be given in terms of x. So for example, what is secant of theta? Secant of theta, I mean, it's 1 over cosine, right? So if you find cosine of theta, which is easier, that was 1 over 2x. And then, I mean, actually we found it before, but you know, secant of theta is just 2x, right? It's just like the reciprocal of everything, but you can redo it here, like, you know. And so, yeah, this becomes 2x. And then what is tangent of theta? Tangent of theta is opposite divided by adjacent. So tangent of theta is just y, but y is root of 4x squared minus 1. And that's your answer. I mean, I'll just write everything in black so that it looks a bit better. And this is like an absolute value, but again, like since even if you put it without absolute value, I don't really care, because it's like these domain things, like we're not really worried about that. So it's more like understanding like what's going on behind the idea that you're doing the right triangle. That's how you're identifying the substitution. That's kind of like the important thing in this type of problems. That making sense? Questions about this so far so good? So again, to summarize, and again, I don't necessarily prefer you to memorize this. Like, I just prefer that you just draw the triangle. But if you want to have like a recipe for something which is kind of like, you know, x squared minus a squared, which is basically what we had here, like more or less, you try with like but again, you don't have to memorize this. Like, the right triangle will tell you what to do. That's like the thing. Like there's only one more example left, and you'll see the right triangle also tells you what to do there. So like you draw the right triangle, and then you're good to go. Like there's nothing else to think about. Because otherwise it's like a mess to memorize all those cases. Yeah. Yeah, that one, I mean, yes, I think for that one, maybe let's say yes. But like yeah, let's just say that. I just don't like also to, that's why I kind of like wrote identities on the exam, because I do hate it when like the exam like depends like the question on something that you just happen to memorize, so like if you wrote it incorrectly, that's kind of like a point, like nothing, like like I don't value that too much, but you could like probably ask me and I'll just tell you what it is. But like it's just like it's like right, like but kind of like almost 60% of the problem is doing the right substitution. You know what I mean? Like everything else is kind of pales in comparison. Like, but yeah, like let's just say yes, but it's not like I'm not too keen, like making it hyper dependent, like because it's like just the very last step. You know what I mean? Like by then, like you have done like 95% of the problem correctly. So, but yeah, let's just say yes to for, but right. Okay, and last one, just to illustrate, like again, and then these are basically the three types of like trig identities. Oh, by the way, tomorrow there's no quiz. There's just in case, like there will only be like this workshop, but yeah, so, the workshop will just be like all these trig integrals that we did last time, and like these new ones. Okay, and for this, you do the same. You call y the stuff involving the square root. And this one even requires less manipulation, because this is already kind of like presented in a way that's Pythagoras theorem already. So again, y has to play the role here of the hypotenuse, and just to kind of break convention, I'll use x vertical, so that to show like there's nothing really going on there that's wrong. Again, like which is this side and which one is this side is completely arbitrary. Like the only thing that you cannot mess with is like the hypotenuse, and that's all. And again, in this case, what you need like a substitute. You need to use like a trigonometric function that involves x, but hopefully avoids y. So tangent is the good one in this case, right? So tangent of theta, and also tangent is nicer in terms. You could if you had put like x here, it would be cotangent, but because like the cos have like negative derivatives, they're more annoying to work with than tan, sine, and secant, right? So the cos, like cosine, cotangent, cosecant always have like negative derivatives. So like that's why if you can avoid the ones with negative derivatives, it's better to set up the triangle so that happens. So that's another reason why in this case it's kind of nicer to put it like x being vertical. But if you use tangent of theta, that just gives you that tangent equals x over 2, or 2 tangent of theta equals x. Perfect. So that's the substitution that we're going to use. So let me write that. So we have that x equals 2 tangent of theta, and dx, what is the derivative of tangent? Secant squared. So 2 secant squared of theta d theta. And once you are here, like again, like if you did the right substitution, the problem has been designed so that everything kind of falls into place nicely. So what is x cubed? X cubed is 8 tangent cube of theta. And then what is x squared? X squared is 4 tangent square of theta plus 4, right? And then, okay, and then what is the x? Dx is 2 secant squared of theta d theta. Okay. So, okay, so 8 times 2 is 16. So there's an 8, 16 tangent cube of theta. I'll put like the stuff which is not inside the square root first, kind of like move it to the front. And then I'll factor out a 4 inside the square root. So I'll put tangent squared plus 1. And hopefully that is one of like the magical identities, right? Which I'll tangent squared plus 1. Again, like I think we used it last time. Oops, here it is. So I'll just copy paste it from here. So you see, like that one gets used over and over and over for all these problems. But if you do that, what happens? So, okay, a 4 will come out as a 2, so this will become 32. Then you get tangent cube, secant squared, and then here, because of the magic identity, then this is secant squared, which then comes out as secant, right? So you get secant here. That making sense? So far, so good. Okay, so what we end up having to integrate is 32 tangent cube of theta times secant cube of theta d theta. Okay. Okay, so let me just check because I'm not sure if I ended up doing this one last time, so I'll just double check in the notes from like last week, like last week to see if we had done this one. If not, I'll kind of like tell you how to do it. Let me go your lecture 7 here. Did we do this? Oh yeah, okay. That was the last example, right? So last example from last time, I'll kind of like copy paste it here. But last example from last time was like this trick that like you take a secant tangent and do like this substitution with u equals secant. So like I'll kind of like remind you like how to do this like in the okay. Okay, let me go back to so like this is like from last time. You do like a u sub where you call u equals secant of theta in this case. So that way the du would become, this would become du, and then you write tan squared using like this formula. So again, like it is like the last example from like the PDF, so I don't want to redo it, but if you do all of that, you'll find, so you end up finding like the same thing as before. Sorry, like put the 32 here. So you get a secant to the 5. I just want to finish it. So like, that's why I prefer to over 5 minus secant cubed of theta over 3 plus c. Like last lecture, I mean, I'll put here last lecture. Okay. And almost done. Last thing is that you want to write everything in terms of x as before. So again, how do you write everything in terms of x? Go back to the magic triangle. Oops. And according to the magic triangle, okay, so you only need to know secant. To know secant, you can do cosine first, right? So cosine of theta again is 2 divided by y, and so secant of theta is y divided by 2, right? That's reciprocal, but like y is coming from Pythagoras theorem, right? So y is like the root of 4 plus x squared, and all of this was divided by 2. And here, like, you know, you can, let me just write it like this. Over 2, so 2 to the 5 is 32. 32 times 5 minus 4 plus x squared 3/2 over, you also have to take the cube here, so 2 cubed is 8, so 8 times 3. And there, I mean, actually, you can simplify this a little bit more, but I don't want you, you know, this is what I would expect you to leave it as. Like, you know, I wouldn't want you to spend more time simplifying this. Like, you know, of course, you can, like, you could do 32 times 5. Like, wait, okay, maybe that one, yes, because that's like 160. But, you know, like, there's like a, you know, if you factor out like some of like the powers here, like, it can look a little bit better presented, but that is not kind of like, you know, the focus of this example. The focus is that for this type of problems, just to summarize, so to summarize, for what was it, for something involving x squared plus a squared, right? You want to use something like a tangent. But again, like the idea is not to remember this, it's just to remember to use like the right triangle. Okay, is that making sense? Okay, so there's only one topic left when it comes to integrals, which is improper integrals, which we'll talk about on Monday. Like, we don't have enough time left to start it, so I'll just kind of like say what will happen. So next time we'll talk about improper integrals. So they will be of two types. Like, type 1 is one of the bounds of integration is infinity. One of the bounds of integration is infinity. Like something like this, for example. And I'll tell you next time what that means. And type 2 improper integrals is where the function wants to become infinity, like, or there's like a vertical asymptote, like, you know, type 2, you're integrating close to a vertical asymptote, integrating for values where a vertical asymptote is present. So like the example here would be something like 0, 1 of like the integral from 0 to 1 of 1 over x, because if you look at this, right, like 1 over x wants to become infinity at x equals 0. So that's kind of like a bad thing. Yeah.
Does this mean it's one of the bounds is where it has asymptote, or there's an asymptote inside where you?
Well, you know, like no, it doesn't, right, like, because here like the asymptote is at x equals 0, which is not part of the domain, but the like, you know, like the function, it is still like the bound, like the asymptote is like the endpoint of the interval of the region of integration, right? So like it would still have like it will still be problematic, you know, because you're integrating something where like the function is trying to become infinity, like, you know, closer and closer to where like the function is trying to become infinity. So that is like another, so it's kind of like infinity is for two reasons, like whether because like the integration that bounds are infinite themselves, you know, kind of go like the region of integration goes on forever because you're integrating up to infinity, or because the function itself is trying to become infinite at some point, right? Like because 1 over 0 is infinite in some sense, right? So it's like the two types of infinity that you could find. Okay, and then I'll tell you on Monday how to deal with that. But let's end here because like that's like an entirely different topic, so I don't want to mix it up with this stuff. Okay.